Yeah, okay, welcome everyone. So today it's our pleasure to have Martina Rama, who will be talking about physics-informed neural networks for probabilistic epidemic forecasting. Yeah, thank you, Martina.
Yeah, thank you so much, Boumedine, for the introduction, and especially for inviting me to this machine learning and dynamical systems seminar series. It's really a pleasure. And today I'm going to show you a little bit, so to give to you an overview on how we can make a machine learning algorithm, in particular a neural network physics informed, to do probabilistic epidemic forecasting. So I would like to remember you. Oh, sorry, I changed this one. I don't know if you see, but it's, let's see. I have already problem.
So what is the problem?
No. Okay. I can just remove it. Okay, perfect. Yeah, sorry. And so, I would like to start to remind you what we have learned for COVID-19 pandemic. So it clearly shown us why we need better models, so reliable models, since to make better decisions and these lead to better outcomes for everyone. So in general, models help us to capture how infectious disease spread, evolved, and impact over the population. And these over time. And in particular, in epidemic, time is everything. So forecasting can really save life. So we would like to do this to inform public health decision and also to anticipate epidemic trends, since this can reduce cases, hospitalizations, and death. And in particular, how we can do it by building really accurate and robust forecasting frameworks that enhance our ability to respond quickly to future outbreaks and pandemics. So what we are going to see now is how we can properly construct this from the beginning, in a sense. So I would like to start with an initial part of the talk that will be focused on the physics, so compartmental models in epidemiology. And in particular, I will focus on SIR model, that is probably the easiest and still the most used compartmental model in epidemics. And then I will provide to you an idea of how we can making a machine learning algorithm physics informed, so providing a methodology overview. And in particular, I will focus on physics informed neural networks. And these two sections set the stage to the last part of the talk that will focus on our hybrid framework to do real-time epidemic forecasting that we it is a PINN-based framework in which we informed the neural network with an SIR model. I just would like to say that if you are not familiar with epidemics models or with physics-informed machine learning, don't worry about it. The first and the second part will be really on a high level, and I will really provide to you a high level overview of the problem. And these two parts gradually approach the third part. So if you instead are a kind of expert on compartmental models in epidemiology and also on physics-informed neural network, I hope you will enjoy the last part of the talk. So let's start from the physics. So what are these compartmental epidemics models? These are mathematical frameworks that are used to simulate an epidemic spreading process into a population. And these are based on the idea of dividing the population into compartments. That one compartment we can think that represents the state of each individual. So let's think about infectious individuals, so infectious compartment. And then we can think about that individuals can move between compartments in according to transition rates, for instance, disease transmission rate. And these compartmental epidemic models are mathematically implemented by ordinary differential equations, or also stochastic frameworks such as stochastic ordinary differential equations, and to take into account also randomness. And these models are fundamental to firstly analyze disease transmission dynamics, seeing also the total number of infections and recovered over time, estimating also key epidemic parameters such as the disease transmission rate, and evaluating also the impact of different public health intervention, and informing public health decisions, especially in a phase before the disease outbreak. So the question is, the problem is that when we use compartmental models to describe an epidemic, we need to remember that they rely on assumptions. So the first one is the mass action mixing. So interaction between individuals within a compartment tend to occur randomly and uniformly, meaning that everyone within a group has an equal chance of interacting with each other. And this, if you think about it, is a simplification of real social dynamics. Another one is that we can consider no vital dynamics, so the spread of the disease is faster than the dynamics of birth and natural death. This means that we can consider the total population, the number of total population constant. And another assumption that usually is made, and that is also in this case a simplification of real dynamics, is that parameters are constant in time. So seasonality does not affect the model. And this is not always the case in real epidemics. And another assumption that is usually made is the horizontal transmission. So the disease is transmitted by contact of infected individuals. So we tend to avoid to model more complex pathways such as vertical transmission in diseases. Now let's focus more on the SIR epidemic model. So this model is firstly formulated by Kermack and McHenry, and as suggested by the name, we are considering the population divided into 3 compartments. So susceptibles, that are individuals who can contract the disease by contacting an infectious. That is an individual who have been infected and that can infect another susceptible. And then we have also the recovered individual or removed, that are the individuals who have been infected and have either recovered or died, if we are considering also death dynamics. So if you, I don't know if you can see my, but this beta SI over N is the incidence in which we can consider beta as the average number of contacts per person per time, multiplied by probability of a disease transmission in a contact between one susceptible individual and one infectious subject. So we can consider it as a kind of law of mass action in chemistry, in which we have a random collision between molecules that results in a chemical reaction, in which we have a fractional rate proportional to the concentration of the 2 reactants. We can formally write an SIR epidemic model in the form of ordinary differential equation system. So with 3 differential equations that describe the change in the number of each compartment over time. So we have susceptible, infectious, and recovered. And in this case, we consider the, if we sum all the variables, so we are considering no vital dynamics in this case. If we sum all the equations, we have that the derivative of n over time is 0, so meaning that the population is considered constant as the initial number of population at the initial time. And we have two transition rate, beta, the transmission rate of the disease, and gamma, that is the recovery rate or the removal or mortality rate. These parameters are fundamental since they are they describe also R0, that is the basic reproduction number or basic reproduction ratio. And it represents the expected number of new infections produced by a single infected individuals introduced in a population of fully susceptible individuals. As we will see, it's a fundamental quantity. And we can also put initial conditions. So at time t equal to 0, we can put the removal 0, and we can also assume that an initial infectious individual, so E at t equal to 0 is equal to 1, and so the total number of susceptibles at t equal to 0 is n minus 1 in this case. So R0 is a fundamental quantity in the sense that it helps to understand the behavior of the disease, and it also helps to study the equilibrium of the dynamical system and the stability. We have that it's a threshold quantity, as I mentioned before. So if R0 is less than 1, nobody will be infected, and so the outbreak will die out. Instead, if R0 is greater than 1, the outbreak will expand, so all the susceptible will be infected. And at R0 equal to 1, somebody will be infected, and there is a fraction of susceptible that can escape the infection. Okay, this is just to provide to you an idea of how we can represent the three components, changing the parameters over time. So we have the three lines. The yellow one represents the susceptible, the red one the infectious, and the green one the recovered individuals. So as you can see, we can start with susceptible equal to at time 0 equal to n minus 1, and instead the infectious are 1, and the recovered are 0. And as susceptible, as the disease outbreaks, susceptible started to decrease. And at the same time, infectious started to increase, reaching at a certain time a peak of infectious. And as well, the recovered started to increase. And we can see it changing the parameters. And so as in this way, also the dynamics change. So regarding the parameters, as I told you, if we know the initial condition and the parameter of the model, we can predict the dynamics entirely in the future. And we can also compute the value of the basic reproduction number, R0. But the problem is when we do not have these parameters. So if data are available, we can sometimes estimate these, for example, using a Monte Carlo approach, which generates a distribution of each parameter. I would like just to provide to you an idea of how this approach works. So it is based on a Bayesian approach. So we have theta, that is the parameter of the data points distribution. We have x, that is the sample. So we can consider it as a set of n observed data points. And alpha is the hyperparameter of the parameter distribution. We can estimate via Bayes' theorem by likelihood. So this is, we can consider a posterior distribution estimated by a likelihood and a prior distribution of the parameter. So MCMC algorithms are used to sample from the posterior distribution of the parameters given the observed data. So for instance, the number of infectious cases over time, considering the likelihood and the prior probability. And by drawing many samples from this posterior distribution, MCMC methods allow for estimating the parameters, in this case of the SIR epidemic model. And this is useful since we can calculate various statistics. So first of all, the mean and also the standard deviation of the parameters, and these provide a measure of uncertainty in the parameter estimation process. There is really a zoo of compartmental epidemic models. So we started from SIR, but we can have, for instance, an SI model in which we removed the removal compartment. Sorry for the joke. And so we put the gamma equal to 0. Or we can have an SERR model in which we are considering also exposed that are infected but not yet infectious individual. We can also have, for instance, an SIS model in which we are not considering removed since recovery does not provide immunity. And so we came back to the compartment of the S of susceptibles. And then you can also take into account the vaccinated individuals. So we can really construct a complex model with several compartments as well as different transmission rates and also different pathways that move the people between compartments. We have limitations when we are using compartmental epidemic models. So for instance, these are oversimplistic. Let's think about the max action mixing assumption that can be really an oversimplification of the real world interactions, especially when we consider social distancing factors or targeted interventions and so on. And also another limitation is that they ignores the individual heterogeneity. So individuals are treated within a compartment as identical. In this case, we are neglecting individual differences in susceptibility, infections rate, or recovery times. And also, there is a limited ability to to capture complex behavior, to capture and also model complex behavior. So they may not be able to accurately model the impact of complex behavior, such as vaccination, social distancing, testing and tracing campaigns, and so on. And numerical methods that implement this compartmental epidemics model have also difficulties in incorporating data that are missing or noisy, also on solving ill-posed problem. And in most of the cases, they are also expensive in terms of cost, especially for estimating the parameters. So until now, we have seen how we can model an epidemic through compartmental models, so ordinary differential equations. And the question could be how and if we can use this physical knowledge to inform the machine learning algorithm. So to introduce physics-informed machine learning, I would like to start with this sentence that came from Karniadakis and colleagues. There is pressing need for integrating fundamental physical laws and domain knowledge by teaching machine learning models about governing physical rules. And in this case, we have to firstly identifying what are the ingredients of physics-informed machine learning. The data and the physical models. These two are combined together and integrated to deal with partially understood uncertainty and high-dimensional context. But let's see the limitations of traditional mathematical modeling. So if you want to reproduce a complex dynamics, probably using a traditional mathematical modeling is not the best choice, since it leads to a less quantitative accuracy in reproducing this complex dynamic. And also computational tools have prohibitive costs and lead to uncertainty. We can think about that if we have really a complex dynamic, we have to making the model complex as well, so probably inserting new differential equations, so new parameters, and estimating these parameters can be really expensive. And then we have also difficulty to deal with boundary conditions, especially if they are missing or noisy, is impossible to solve. And also to incorporate multi-fidelity or multimodal data into physical models. From the other side, machine learning emerged to solve some of this problem. So it explores massive design spaces, so it can identify multi-dimensional correlations and also manage posed problems. And in particular, deep learning, if you think about deep learning, it can extract relevant features from a huge amount of data. But machine learning approaches have current limitations as well. So especially when data are few and noisy, the accuracy and the generalization capabilities decrease. And also the extraction of interpretable information is poor. And usually there is no explicit learning of the physics of the problem. And this could lead to also system laws violation. Also in these cases, the computational cost can be really high. So to overcome these limitations, taking the best from the two perspectives, hybrid approaches has been developed. In particular, physics-informed machine learning emerged as a novel framework. So the question is how we can make a machine learning algorithm physics-informed. One possibility is with observational biases. So through data that can be embodied physics or with data augmentation procedures. Another possible approach is with inductive biases. So modifying machine learning architectures in such a way that they can incorporate prior assumptions. And the last approach is with learning biases. So forcing the training phase to converge to solutions that are more focused on learning the physics. This is done usually by by choosing an appropriate loss function. So these are just a few examples of the three categories. I don't know if you are familiar with convolutional neural network, for instance, or graph neural networks, or equivariant, covariant neural networks. You are working with modified neural networks in such a way to preserve conservation laws. So you are working in the inductive bias approach. And instead, regarding the physics-informed neural network, are a methodology considered as a learning bias approach. So I'm pretty sure that probably almost half of you can put itself in one of these three categories. So is working with physics-informed machine learning algorithms without probably even knowing. And now let's focus on physics-informed neural networks. So these are methodologies. This is a framework that emerged as a novel methodology to take advantage of both deep learning frameworks, such as neural networks, and of the physics of mathematical models, so such as partial differential equations. And the right domain of applicability is when we have few and noisy data, but we also know some physics about the problem. So for instance, the dynamics of the system. From 2018, the literature is becoming full of paper and reviews about physics-informed neural network in several domains, and for instance, starting from the engineering, environmental, biology domain, also chemistry, and so on. And so let's formalize a little bit what are these physics-informed neural networks. these are universal function approximators as neural networks that embody the physics in the neural networks through parameterized partial differential equation systems, so such as this one, in which we can also have an initial condition, and lambda is the parameters, and f is the differential operator. The solution U models a time-dependent vector field. And the problems that we can tackle with physics-informed neural networks can be the forward one. So if we have the model parameters, find the unknown solution of the problem, U in this case, and the inverse problem. So given some observation, finding the optimal parameters that best describe the data. So regarding the forward case, we have to start with the construction of a neural network that is physics informed and that approximate our solution, so the solution of the system. For instance, the one that I showed you before. And this is done by writing in a precise way the loss function with a so-called residual function, that is this one, that as you can see is the homogeneous form of the partial differential equation or ordinary differential equation system. So is this part. And once we have write the residual function, we can really construct the loss function of the physics-informed neural network that has 3 components. The data loss function, that is the standard mean square error of the neural network. So is the approximation error that the neural network computes to be as close as possible to the real solution in pairs of data points, so the training set. And then we have a physics endowed loss, that is the core of the PIN, that is written by the residual function, as you can see here. In this case, in R, so-called collocation points. And as you can see, requiring that this loss function is approaching 0 is equivalent to requiring that the residual function is 0, and so that the system of the ordinary differential equation is satisfied. And finally, we have the initial condition loss function. So this is done to force the neural network to satisfy the initial condition, and we can also have similarly the boundary condition loss function. So as I show you, the physics-informed neural networks are based on this regularization procedure, in which we are inserting a regularization term into the loss function that drive the neural networks to be as close as possible to the real solution of the physical system, as well as fitting the data and preserving also the initial or boundary conditions. And in this way, we can also solve the inverse problems simultaneously. This is done by considering the parameters that we would estimate as the neural network's parameters, and then through backpropagation, updating the parameters as well, finding the best ones at the end of the process. This allows us to benefit from simple feed-forward neural networks and leveraging few layers and few neurons, and using also small amount of data. If for Boumediene is okay, I can take a break here before moving to the last part of the talk that will focus on our contribution. So if someone has a question on this initial part, I can answer directly. Otherwise, I will move it.
Yeah, sounds good. Yeah. Any questions or comments? Or yes, seems not, so you can continue if you want to.
Okay. Yeah, I can continue.
Okay, thank you.
So no worries, thank you too. Okay. So the last part of the talk will focus on our contribution with joint work on forecasting seasonal influenza epidemics with physics-informed neural network. And in particular, I would like to show you the entire process that we made for constructing this framework. So what is the idea of this? We would like to learn epidemic dynamics to do real-time forecasting. And how we did it by constructing a physics-informed neural network that is informed by an SIR model, and leveraging this hybrid methodology to do forecasting and also probabilistic forecasting. And the steps are firstly efficiently learn epidemic scenario close to real cases. This is we call step 1. And this is done in such a way that from few and noisy data we can infer the epidemic parameters of the dynamics, and finally forecast epidemic dynamic with also uncertainty analysis. So to do this, I would put all the things that we have seen before in the first and second part of the talk together. So one question could be, since the literature is really increasingly and starting to be increasingly extensive and pervasive about physics-informed neural networks, one question could be, did they reach the epidemics field? And the answer is absolutely yes. These are just few works on physics-informed neural network for epidemics. But one thing is that these works could have some limitations. So they are limited on the application of real-time epidemic forecasting. So they are more focused on showing the accuracy in performances on synthetic data or on epidemic forecasting, but not really on real-time. And the frameworks usually are not so optimal in a sense, since they are fully exploitation the PINN's potential, and so also solving simultaneously the forward and the inverse problem. But these could lead to rely on extensive use of neural networks, also used for solving the different tasks. So one, for instance, for solving the solution, and others for estimating parameters. And for this construction, the retrain is always needed. So every time we have a new observation, or every time we change the epidemic scenario, we need a retraining of the neural network. That could be expensive. And also, almost all of this work have no uncertainty in quantification. And this is a problem that is given to the fact that to the fact that we are using a neural network, so that provide a deterministic output, and so one single trajectory, and we are not able in this sense to do an uncertainty quantification of the forecasting process. So to try to overcome this limitation, we built this SIR-in, so physics-informed neural network informed by an SIR model that is really an hybrid framework in all the process. I will show you in few seconds. So the first part is that what we did is that we used a physics-informed neural networks to approximate, so to learn a SIR model. So we have already seen this model, the SIR, in which we consider no beta dynamics, so constant population. R0 is beta over gamma. And the first things that we did is to rewrite the system in a compact vectorial formulation, as I showed you before, in such a way that we construct the residual function. So that is a derivative of u over t plus f, putting the differential operator in the left-hand side of the equation. U is the solution that is written in terms of SIR components, and that depends on the parameters. So on doing this, what we did is really to construct a physics-informed neural network that approximate the solution of a SIR, ordinary differential equation system. So the neural network has three input, the time component and the epidemics parameters. We provide, so in this case, we provided the training set with ranges of times, beta and gamma. And we write the residual function, as I showed you before, in such a way that we can write also the physics-informed loss component, and also added to the standard data loss component of the neural network. Regarding the parameters inference, instead, we did not leverage the fully potential of the PIN, since we have constructed such a framework. But instead, we solved the inverse problem via a Markov chain Monte Carlo methods. So, as ingredients, we have the pre-trained our pre-trained neural networks, so UN, and then we have the data that we can assume to be a function of time and also epidemic parameters, beta and gamma. And finally, what we have to do is to select a time window of observation. So the data that we have could be the observation of infected individuals at some time, precise times. And then we select the parameters to infers. So in this case are the initial times at which we started to observe the data and the epidemics parameters. And these with also provided bounds for these initial conditions and prior distribution that are uniform. And then also we determine MCMC settings. And we run this Markov chain Monte Carlo method to obtain a Markov chain of the estimated parameter. So in this case, we inferred the epidemics parameter via Monte Carlo Markov chain, as I told you, that is informally, it's like to solving a minimization algorithm in which we would like to find the best parameters, minimizing a loss function that we consider as the mean square error and the difference between our data that are a function of G and the output of our neural networks, a function of capital G. In this case, we can consider the easiest example is when, for instance, we have G that could be the infectious individual. So capital G can be considered as a function that put the first and the third components equal to 0, so the susceptible and the recovered component. Instead, the infectious component equal to 1. So we can have a sort of coherence with the function of data. And for instance, another example is when we have influenza-like illness incidence data. We can consider this function of data as the difference of susceptible individuals over time, multiplied by 1,000 and divided by the total number of the population, since it is an incidence. And in this case, we have to consider the function G, capital G, of our neural network output to be coherent. So we have the difference between the susceptible, so outcome, so 0 component, in times, so consecutive times, so T, J minus 1 and TJ. And this multiplied by 1,000, and we can avoid to divide by n since our neural network output contains the normalization over the population size. So finally, we have the forecasting part. That is probably the crucial part, but in this case, the easiest one, we can say. So we have just to select a forecast time window of observation. So how much we can, how far we would like to go in the future. And then we evaluate our pre-trained SIR informed neural networks on these estimated parameters until the fixed future time. And we can consider the mean model outcome as the mean solution that came from the first observation at t0, estimated time, to the last future time. Remembering that we are, for the forecasting, we are also leveraging the MCMC algorithm for the estimation of parameters. So we are doing a probabilistic forecasting with prediction intervals. So let's see some results. We took as a case study the Italian seasonal influenza data that are provided by the Italian National Institute of Health. And in particular, these data are provided weekly and are in terms of influenza-like illness incidence. So as I showed you before, we can write the data in this form. So as a difference of susceptibles over time, normalized. And we put ourselves in the same condition of the InfluCast hub. That is a forecasting challenge 4 weeks ahead. As you can see, this is a screenshot of the site. And they have the data until a certain point, so observation, and then the challenge is to forecast 4 weeks ahead with the prediction interval of 50 and 90% respectively. So these are our results. I'm going to provide to you just the results for the most recent season, but if you want, I have also the others for the previous one. And so as you can see, we have that the initial phase, okay, the blue dots are all the observation, and the highlighted one are the observation that are used to estimate the parameters and then to do forecasting on the next stages. And the green line, the green line represents the mean forecast outcomes, and also the prediction intervals are shaded in green and orange for the 50% and 90% prediction interval respectively. So the initial phase of the forecasting, as you can see, is pretty estimated accurately. And also the peak is estimated in some way accurately. The time of the peak, especially, is not too far from the real one. And also the maximum ELI incidence estimation. And also the decreasing phase is estimated, the initial part is estimated quite well. As you can see, the mean model outcome almost fit all the future data. And we can also observe an interesting thing that if you see here, we are at the 5th week. And in this case, the model is not able to accurately predict the increase in the ELI incidence curve. But this is really challenging, and also the other models that participated to the forecasting challenge, in the InfluCast one, they deal with this problem, especially if you based on neural networks. But if we moved a little bit far, so at week 52, our model seems to be able to predict that with a certain probability, it can be an increasing in the incidence in the incidence function in such a way, understanding that the peak at the week 51st is just an initial peak and is not really the real one that occurs at week 4. So we also would like to compare our results with the ones in the Fiandrino and colleagues' work, so with the other state-of-the-art forecasting epidemics models for seasonal influenza. And so we implemented the same metrics. First of all, the absolute error. So this is the absolute value between the median forecast and the real observation. Then we, for a certain time, then we have also the weighted interval score, that is an approximation of the continuous ranked probability score. And it is based on the fact that we are generalizing this interval score to 11, actually, 11 physics, 11 prediction intervals, okay, in this way. I'm not going to enter in the details of this formulation, but if you want, we can talk about it later. And this is important since it also it's considered the forecast median solution, so the absolute error in a sense, and also the prediction interval error that we made. And lastly, we have the coverage error. So this is measure how a model is calibrated, and is defined as the fraction of time of a prediction interval contains the actual observation. So for instance, observation will be included exactly 90% of the times in the 90% prediction interval. So let's see the quantitative results about it. So first of all, we compared our approach, our framework with the baseline model for the forecast for the 4 weeks ahead forecasting. And these across the 2 seasons of influenza for all the rounds that we have. So these are all the simulation that we take into account. And as you can see, in terms of mean absolute error and weighted interval score, our model outperformed the baseline. So the values are lower, okay, in both the cases, so both the seasonal influenza. And regarding the coverages, although the coverage values remain below the ideal one, so for instance, in the case of the 50%, the ideal value is 0.5 and 0.9 regarding the 90%. So these values remain below the ideal one, but are still quite good, especially when we are working in the for the second season. So this means that for the second season data, our model is better calibrated. And if we see the results of comparison between our model, so Serene and the Influcas models, the other Influcas models, included the ensemble models that take into account all the models, predictions, and the baseline one. We can firstly focus on the relative mean absolute error and relative weighted interval scores. And we can see that here, one point is that here all the results are considering pairwise predicting performances of the models that participate to the same round, and also are then normalized by the baseline model. So the baseline is 1, and values below 1 means that the model is more accurate. So the performance are better. Instead, if are greater than 1, are worse. So what is the idea? That our model seems to be in line with other Influcast models predictions and results. So in the case of relative mean absolute error and relative weighted interval score, we can see that is a little bit higher than the baseline. But for instance, in terms of relative weighted interval score, it ranks 5th on the other models. So it outperforms other models such as a semi-mechanistic one, and also mechanistic 1, mechanistic 2, and also this, so semi-mechanistic 2 and statistical 1. And instead, in terms of coverages, so also in this case, the values remain below the ideal one. but these values are still in line with the other models. So for instance, it auto-performs in this case, in the case of coverage 50, the semi-mechanistic 1, and also the mechanistic 2. And in terms of coverage 90%, it auto-performs the semi-mechanistic 2 and also the statistical 2. And semi-mechanistic 1, sorry, I missed it. So what we can say in another thing, one thing that I don't think I told you is that these results are just for the season 2023 and 2024. Since this one, for this one, for the most recent one, we have still no results about it. And we also try to perform long-term forecasting, so 10 weeks ahead in particular. And as you can see, our model for the season, in this case, 2024 and 2025, so the most recent one, the model seems to be accurate in a sense regarding the 90% coverage. So the prediction interval, it covers almost all the future data. These are just 4 panels about the critical phase before the peak. And as I showed you before, also in this case, we have this trend when we reach the week 52nd that our model seems to capture and to have an idea a little bit of what will happen with kind of low probability, but it's still quite good results considering the other models' predictions. And also the peak phase is estimated accurately when we reaching it. So when we started to reaching. So these results are regarding seasonal influenza validation. And we can see that regarding the short term, so performances are in line with these influx models. And our model outperformed the baseline in terms of absolute error and weighted interval scores regarding the national results. So we can, we can conclude that its implementation will contribute positively to the future forecast. So for instance, for the ensemble models. And regarding the long terms, as we have seen, it is able also to partially capture the trend and the peak time. And this is a great result if we consider that usually neural networks fail on long-term predictions. And so to conclude, we developed this SEER-informed neural network framework that is an hybrid, efficient and accurate surrogate for real-time epidemic forecasting. So in particular, to summarize, we can efficiently capture the dynamic of different epidemic scenarios in such a way that from few and noisy data, as we have seen, we can infer, firstly, the epidemic features, and secondly, we can do forecasting, also with uncertainty quantification. This is done with just one neural network, one physics-informed, and that is trained also once. So this with small amount of data and also low computational cost. And for this generalization capability of our physics-informed neural network, we are thinking about to apply our framework to other SEER-based models initially. So for instance, for our epidemics, or also non-opinion dynamics, and also to extending to other PINN-based methodologies for do forecasting. So for instance, we can consider more complex social dynamics with also addiction of behavioral factors. So I would really like to thank to my collaborators. This is a jointly work. So Gabriele Santin, Giulia Cencetti, Michele Tizzoni, and Bruno Lepri. And I would like to conclude. Thank you all. And so questions are welcome, and I will be glad to answer if you have it. This is the QR code of our paper on the archive that we just submitted to Epidemics a few weeks ago, actually. And so thank you again.
Yeah, thank you very much. Thank you. Any questions or comments?
Thank you, Martina. I guess I do have one, if I may.
Yeah, sure. Please. Thank you. Yeah.
Yeah, thank you.
My question is, I didn't follow all the, I wasn't able to follow the entire explanation, but what I get is that the mechanistic models are still somewhat doing better in predicting, in forecasting 4 weeks ahead. So my question is, what is the future you foresee? So they use the actual application you foresee for these physically informed neural networks in the context of epidemics, and whether, for example, so you showed that I don't know, 9 weeks ahead you're still doing pretty good. How is that compared to mechanistic model?
So thank you, Lorenzo, for the questions. So first of all, yes, it seems that this hybrid approach seems to be promising in a sense for also to forecast, because we know that on the accuracy and performance as a surrogate model to mechanistic one is good. So physics informed neural network are good in this way, but on forecasting the literature is not so this field is not so explored. So we try to do it, and it seems to have quite good results in this sense. And yeah, regarding the comparison, actually, if you think about it, all these models, almost all these models of the InfluCast that participate to the InfluCast hub are based on mechanistic models. So as you see, or at least are semi-mechanistic in a sense, but are really traditional approaches. So no one is based on neural networks, for instance, this one. And so this could a comparison in a sense for this kind of seasonal influenza forecasting. It could be really a great thing to see how well it will be performed also on other tasks, and also compare with other methodologies. So I agree with you in this sense. So for me, I really would like to see this. And so also with other epidemics, as you mentioned, so this could be really a good thing, especially because this algorithm is trained once, so you can really try to generalize it to other seer-based epidemics. And also we generalized on across different seasonal influenza, across different seasons of the influenza, but we can do it also on other seer-based models easily. And so, yeah, I would like to see it too in this sense. So, yeah, thank you.
All right, thanks. Other questions or comments? Yeah, it seems not. Yeah, thank you, Martina, for the nice talk, and thank you all for coming. And yeah, that's all. Thank you very much.
Yeah, thank you all, and thank you, Boumedine, for the invitation again.
Yeah, thanks again. It was nice having you here. Yeah, thank you.
Yeah, thank you.
Yeah, thanks
Bye-bye.
everyone. Bye.
Bye.